It's a really pleasure to be here. And I'm truly impressed with the collaboration and the spirit you're doing. I know how not easy that was. I would almost say word hard when I was doing that. So it's a pleasure to be here, meet many of you, and many of you I met before, and see how you're doing and how you're organizing that. And it'll be really nice to share that with you. CPES, Center for Power Electronic Systems, that's why I added, that's a different perspective. I'll say a few words about how we did it at that time, and then I'll talk more. Actually, most of the talk will be what we have been doing since then. And it is similar to yours, going from devices to the system, because that's what actually power electronics is, and that's why it is so difficult and not so many people going to do it, because it's so broad and deep at the same time. And I'll share some of feelings and experiences with you about that. So we got that center, we started about 20 years ago, asking this question, what is the future of power electronics? And the power electronics has two words. One is power, the other one is electronics. So are we more like electronics, which has a Moore's law, and every year and a half it's half the price or twice the performance for the same money? Or is it more like power, which actually did not change much in the last 50 years? And even in its peak, when we were electrifying the world, its Moore's law was about 5% every year and a half. So why? Well, there is physics, but there may be other things. And so that was the question. What is the power electronics? Can we follow this, or be somewhere in between? And the vision we had at that time, we tried to sell to NSF, was to enable unprecedented growth of power electronics industry by developing an integrated systems approach via integrated power electronics modules. And then we put even some impossible numbers that we will improve the quality, reliability, and cost, and reduce the cost 10 times in 10 years, all of them at the same time. Well, that did not exactly materialize, but it was a nice thing to say. And this actually follows very much what we heard yesterday, John Clare's approach to fun about structural and functional integration. Actually, these words are exactly the ones that we kind of try to sell and said, we'll make this 10 times better, this 10 times better, this 10 times better. The only difference is we didn't move away from Lego. We proposed actually to use the Lego approach and solve everything in that way. So there is some difference there, but in many ways, the concepts were very similar. So to do that, we actually did get the funding from 98 to 2008, 10 years program. This was 5 universities, so it was much easier to manage than 10 universities you have and growing. You may have 20 by the time you finish, and that's an interesting challenge in itself. And we were doing everything from devices up to the applications, and the core was this, how to put the things together. And another nice thing was that we did have a strong industrial support from the beginning, and we are continuing to have that. So we received a total in these 10 years about $40 million, and this is the cost of this slide. This slide will tell you what we did with $40 million. So it's 10 years. We started first year and a half kind of establishing benchmarks, looking at the state of the art in the devices at that time, also components, magnetics and capacitors, and then looking to 2 applications which are all the time in our mind, drives and the power supplies for datacom systems, and how there was already motor converter integration that was built by Wisconsin, and then state-of-the-art converter that was built at Virginia Tech. And then started looking at new technologies, silicon carbide that was early there. Also packaging, avoiding wire bonds, that was kind of a holy grail. If we achieve this, everything will be 10 times better. We didn't quite achieve it, and it wasn't 10 times better, but still it was nice to believe at that time. So we started embedding sensors and other things into the modules. An interesting thing that we started doing that time, really demonstrating how you integrate the passives themselves. So you could integrate capacitors and inductors into electromagnetic structure, or even transformers, and see what benefits and penalties you get from that. And then how that could impact the system. So this is an explanation, a comparison of the state-of-the-art power converter that would have 60 components, something that has less than 15 components, because you integrate many things. You still have the same functions. They're just being built together, and causing the problems by putting them together, but also solving some other things. We also started then after that looking at new technologies that were coming up. So nanosilver for sintering for the die attach was developed at that time, still being used in different forms by us and many others now commercial. First GaN hemp with 600 volt breakdown voltage was developed in that center by people from RPI, Paul Chow, in about a little bit more than 10 years ago. Also different sensors like giant magnetoresistive sensors. We were the first ones, Wisconsin, to start doing that. And then looking how you actually go and build integrated ballast for the lighting or integrated machines, which we were able to demonstrate at that time. They say, did you really improve reliability 10 times? Well, I must say first that we didn't know much about reliability, and we learned a little bit about it through the 10 years, but not too much. We did improve reliability because these first modules never survived more than first testing. And these ones here were able to be turned on and turned off even more than 10 times. So it was obvious improvement over 10 years. So yes, we did achieve some of the goals, although the cost, I'm not sure. But at the end, we really started looking much more about the impact of these technologies on the systems. And that's coming back now. At the end, it is the systems that matters. I mean, besides, if it's not us in this room and similar people that know what we are talking about power electronics, at the end, the people that care about application, and not even application of a converter. It's application of a big system. So that's what one needs to look at if you want to keep attention. And that's what I'll try to somehow play in this presentation. That's one of the lessons we realized during this 10 years thing. Anyway, narrowing down, so that was then. Now I'm still in Virginia, and that's where Virginia Tech is. Just a little bit southwest from Washington, and then a little bit more southwest from New York. It's a nice mountains. It's a small place. There's 5 of us guiding 40 PhDs and still covering a lot of ground. From the components, integration, still packaging, EMI quality, and then applications is really kind of 3 big groups. Vehicular power systems as power systems which are kind of self-contained, autonomous as I like to call them. And then another type also which are becoming power systems is datacom. It's a data centers, but even a simple cell phone can contain up to 10 or 15 power supplies, which is amazing that it's true, but it is true. And that they are power systems in themselves, and many lessons actually could be cross-carried from ones to the others. And then looking to make an impact on big power and the grid applications from the sustainable energy. So looking something in the middle, and another reason I chose this as my introductory slide on a technical was published by some guys who you may know, Pat Wheeler and John Clare. And actually that's how we got to know each other so well, because for about 10 years, starting 15 years ago, we were very strongly involved in exactly the same projects funded by same sponsors, industrial, which was aerospace systems. And this is a good example of the big change that has happened and that we are thinking is going to happen everywhere, and maybe even on a grid, but sometime in the future. Where in airplanes, you use the fuel to propel the airplane, and that's where most of the power is going. But about 5% or less is used for auxiliaries on your airplane. And that used to be, or still is in 90% of the airplanes, or more than 90, that you use about 200 kilowatts for electrical, and everything else is then done by taking the bleed air, which is basically just compressed air after the turbine, to pressurize the cabin and do some other things with pneumatics. Then have pumps for the hydraulics, for the motion of all the surfaces, fuel pumps and so forth. And what's happening today is actually all of that is electric. So 787 Boeing airplane, that's the program that really pulled the Nottingham and our group together, everything is electrical. And now suddenly you have more than 1 megawatt power generation on a medium-sized airplane. This airplane is quite a bit smaller than 380 or 747, but has about 3 to 4 times higher power generation capacity than those big monsters. And so that's where electrical does, that's what systems do. Why do they do that? Because power electronics is cool? Well, probably there is a reason for that, but at the end it's going to stay and not die, this approach. If it's going to be actually cheaper, more reliable, more convenient, and gives performance things. Not on a converter level, but airplane. Airplane will be cheaper using less fuel and being able to do things more comfortably than what it was able to do before. So that's kind of a thing that's systems to devices. So what's characteristic of these MEA, more electric aircraft systems, and 787 specifically is a kind of a mixture of the loads and supplies and the voltages and the currents. Although there are standards, there is not one voltage, there is not one frequency, there is not one type of distribution system. There are as many as needed. And how do you interface them? By using a whole bunch of converters. And this is an interesting thing, you know. We are used to having converters to convert the loads, motor drives and power supplies and so forth. Why do we do that? To deliver power to the final load, consumer of energy, in the best possible way to optimize its performance, right? And over the last 50 years, that's the story of power electronics. Last 10 years, we have been doing more and more on the source side, like battery chargers, dischargers on airplane, power converters from variable frequency to the constant frequency or DC for renewable energy and so forth. What has happened in these hybrid systems that you also have these very funny converters, which I call power distribution converters, which just connect, let's say, constant frequency with the variable frequency AC systems, or DC systems of different voltages, DC and AC, and actually, in some cases in the aircraft, but in many cases in other applications, actually these are bidirectional. So energy actually goes both ways, and you can't say which is a primary, which is a secondary bus. So this is a very interesting approach. This is kind of like internet energy is going from everywhere to everywhere, like information is going from, there is not clear who is the source and who is consumer of information. Here you don't know who is. And that changes a paradigm. Power electronics is asked to do many more things, but also give an opportunity. And as I mentioned, this is happening in autonomous power systems like airplanes, ships, cars, trains, but it's starting to happen in systems connected to a grid as well, mostly with renewable energy because they cannot run without these things. And then in a microgrid, you're having very similar things to this. So that's what I'm going to talk about. So I'm using this as an example of that such a power system, which could be isolated or maybe connected to a grid, which is a microgrid or autonomous power system, as an example. So this is a system, okay? And it's, as I mentioned before, it's characterized by electric energy is provided by power electronics converters, it's consumed by power electronics converters. So it's just power converters talking to each other, okay? So it's cool. We are now the emperors. We control everything, but that also means we can screw up everything. So even when we are building or when we are utilizing it. So this works in places that it does in a transportation because it actually does produce reduced size, weight, and fuel or energy consumption on a system level, in an airplane, in a car, in a train or a truck for the mining or off-road applications and so forth. And so at the end, it is a lower cost. No, not the power electronics. Power electronics or the power system is probably 2 to 3 times the cost of the original one. But airplane is lower cost. Flying it or utilizing energy over time, or car is, or train is. Okay? In trains, this has been figured out about 100 years ago, but in others, not so. So when you put all these things together, then one thing is that not only that each one is doing well or is small or is efficient, but that whole system is. And that is kind of an issue, and that's what I'm be talking about. Whole system, but whole system how? One is, you know, that you really do deliver power from where you want to where you want it to go, and that's how you see the efficiencies. So that's what I call it, the line frequency, and that's where the real energy goes, so DC or whatever frequency you're using, where all the energy flows are, the primary ones. And these are intended. You build a system to do this, and you build the converters to be small, efficient at these frequencies. And that's mostly what you were talking yesterday, and that's mostly what we power electronics guys do. But also, there's unintended things. This thing has to work together, not just doing this, but also not doing something else. So the frequencies between these and the switching frequency still has to behave well. And also, these are all switching converters, which we found is the best, most efficient way to do it. It also has to not talk to each other in an unpredictable way at very high frequencies. And how to put these things together, that kind of ends up being, you sell the system to do this, but then you have to worry about all of these. So that's what I'm going to talk about today and give you some feeling of what are we playing with on that breadth from all the way to the conversion where we need to worry about devices to all the way to here where we really need to look at the system. Each converter, each device, doesn't matter. So let's start with the first one, and here I'm just going to have 2 slides just to mention we're doing some of that, but actually this presentation will be done by Richard just after me, so this is kind of introduction for him, why it is so important. So yes, silicon carbide will do everything for you. It has a wider bandwidth, and that's why it's called the way it is called. But the big other things are that actually, this one you may not want, but what you get because of it, that you do get a critical field much higher, so you can get the ability to conduct the currents and the temperature at much higher voltages with not too much penalty. And because of that, you could go with higher voltages having the FET structures or MOSFET structures, which didn't work well. You had to use bipolars in silicon to achieve the same types of losses. And these things are now happening, and they're commercially available, and they're penetrating the systems. So let's say you have a silicon carbide devices, you have reduced conduction loss, you have reduced switching loss, or you have high temperature operation. With 2 caveats, if you do have high frequency passive components, and that's, we did not spend enough time doing that, and if you do have high temperature packaging, then you may be able to get all the benefits by going smaller passive sizes, smaller cooling, and then overall higher density and efficiency. So there is still work to do, but on both sides. These devices are very early, as well as GaN. And then how to really build them into the system, there are still issues that need to be done to make that well. We don't do work on the devices, but we do consistently destroy them. So manufacturers send to us anything they have, and we use to destroy them. This is the work by Christina, actually. That she got devices from 2 years ago from everybody who was making 1200 volt silicon carbide MOSFETs, devices, not MOSFETs, JFETs, MOSFETs, and BJTs, and tried to destroy them and see why they failed and how they failed, and I got some nice comparisons. So these are good things to see what fits where and how. And we keep doing that. Now she is starting to do 10 kV stuff, and we thought that's very dangerous. She might kill herself or somebody else, so we sent her here, and she'll do that work with Mark. But this one shows, for example, on resistance of the MOSFETs, and they do really behave very nice. What is the nice thing there is that you would, as you would expect, that bipolar transistors have a lower voltage drop than the MOSFETs. That's kind of because you have injection conductivity modulations to be expected. But when you look at the total switching loss, there is an interesting observation that those bipolar devices actually have the switching losses also comparable to MOSFETs. That's unusual, and that's specific for the wide bandgap, specifically silicon carbide, because the physics is not exactly the same. It's analogous, but not the same. So these are some things that you learn from the application point of view, and then hopefully the device guys, and Richard is going to tell us why this is this way and what other options exist there in the future. But you know, big takeoff from these 1200 volt devices is that they are, they have lower conduction losses than the MOSFETs at higher voltages, silicon MOSFETs, and they have a higher switching frequency than IGBT. So at 1200 volt, they should give you benefits. The question is, do they give you system benefits of the factor of 5 or so, which is the cost difference between them? But cost difference is not so big a deal because cost difference 2 years ago was 500, and now it's only 5. So we're going in the right direction. But we have played with these for a long time, and this is the thing that was sponsored by Boeing when we were looking to use a silicon carbide in a motor drive system where we'll have active front end, inverter, and do NDMI filter and do complete conversion with this in order to reduce the size. And the idea was to high temperature modules. This was not to work in high temperature environment, but actually allowing the converters to work at devices to work at high temperature heatsink could be smaller. So that was kind of question how much we could gain from that. And, but although at that time we already had the silicon carbide JFETs, not MOSFETs really, which we could use reliably, but we did have JFETs. But nothing else was high temperature, so we had to develop our own high temperature packaging. And we were able to do it using some of the techniques like silver nanopaste was used for attaching and some other more traditional techniques. Then we put it far away, the gate drive from your devices, because this will be 250C, where this will not be more than 70C. So you have to provide some spacing in between. So you can save maybe in weight, but not in volume, because there's some volume issues isolating that. A nice thing about that program was also that we were developing high temperature motor. This is using actually permanent magnet lateral axial flux thing that was developed by Tom Lippo in Wisconsin. And then this is the one phase leg, and then you put 3 for this and 3 for this to have 6 of them running around the motor. This is just a fan. The motor, this motor will come at the bottom, and these are the things around. Now, this is actually a low temperature prototype that we built in order to see functional integration. And then to see structural integration, this is a high temperature drawing. And then we built a high temperature system. It's here. And this is how much we show to save. So it's not that big. It's about, whatever, less than 20, 15% in a weight, because actually just the thermal management system, fan, and the heatsink size decreased that much. Everything else was about the same. We were able to push the frequency at 70 kilohertz and reduce the EMI filter. This is hidden in the middle. These worked well, and we were able to deliver this to Boeing to play and have fun with it. We followed that one with different topologies, putting converters in parallel, and you were talking about some of these things yesterday. Then integrating the front end by integrating EMI and front end boost inductors into one functional and structure, and I'll talk a little bit more about that. So here are 3 phase legs for one converter, 3 phase legs for other converter, integrated boost inductors and EMI filter for the front end, and then you put everything together with a power, with a controller, and still get everything working. Now, this is at 15 kilowatts, we got over 6 kilowatts per liter. You are targeting 5 times that. Well, good, but this is including a cooling system and a filter and everything else. So there are still, I think you have nice things to do, but the big thing there was that this heatsink and there are fans underneath that are extremely small if you can allow this large gradient. That air is 70 degrees C and the junction is 250. So then, your all thermal resistance is whatever it is, the total heat flow is much higher with that large difference. Another program which was actually funded by Rolls-Royce guys, and Kevin just left, but he helped us at the end of this program have this running. It was to look at use high temperature when the whole thing is in a converter. So now a converter in a high temperature environment is in a jet engine environment. And in that way, they would use for a starter generator to start the jet engine, and then once it started to produce a DC. So this is 540 volts, and here is a variable voltage up to 230, and variable frequency from 0 up to 800 hertz. Again, now everything is high temperature controllers, processor, as well as power stage and the filter. Again, looking at the packaging, just focusing here on the module. Since we have to design complete things because you can't buy any high temperature modules, then you can also optimize your commutation loops and other things in order to be doing high switching. Develop some prototype, get very nice, optimize the gate drives and everything else. So we used gate drive resistance of 0. This is with the MOSFETs. That's one of the holy grails that I say. Whenever they try to slow down GaN or silicon carbide in order to not oscillate too much or not blow up and not do this, you are defeating the purpose. They go back to your IGBTs and forget it. Keep it there. It's tough. It takes a year and a few graduate students, but it can be done. And then you can actually achieve switching losses, for example, 10 to 20% of equivalent IGBT with the conduction losses, also better or comparable to IGBT. Then again, high temperature operation. In this case, we tested it all the way to 200C. And then making, this is the painful piece. Then if I want to make a power converter, this is a 50 kilowatt, and we would parallel 3 of those for starter generator application. you have to actually make a whole bunch of modules, and you keep blowing them up, and you keep them making them up, and they should have similar characteristics. So there are 3 of those in this converter with the high temperature sensing and gate drives and control, high temperature capacitors, everything sitting on a cold plate. The ambient temperature here is 200, and cold plate is 70 degrees, liquid cooled. A lot of materials, a lot of things, and a lot of things to figure out to make this work. These are the demonstrators. At the end, you know, Rolls-Royce is never going to make it. And actually, at the end, when we finished it, this was deliverable. It says, why don't you keep it and keep destroying it and learning from it? So, yeah, what are they going to do? They just needed the lessons learned. Okay, so you do this high temperature, everything is work. We proved it works. And then something that, you know, some people here that work on reliability figured it out. If you go in, like, in these environments, cycle this between -50 and 200 degrees C with about less than 1 hour going cycles, then, you know, the question is how long it's going to last. And it's going to last very long. It's even 20 cycles. So this is like our improvement originally. So you do it 20 times, and then you have to replace it. The thing just falls apart. Delamination between ceramics and copper. And this is the nice work that I heard here that I'm hoping Mark is going to do with fiber composite instead of using the standard DBC and solve everything. We had to do a crack of it. This is a pun, right? So this cracks, but we had to do a crack of it, how to do it on these examples, because we need even more than 10 or 20 times just to test the system, and these things were falling apart. So you have the ceramic, you have copper on this CTE, thermal expansion coefficient mismatch causes these cracks. There have been shown that ways that you can reduce the stress, and this is through the analysis that was shown here as well, with stress and strain analysis, by, you know, grading this transition and by stepping it. And then something that was also published that you could seal these edges and then get something better. But what was interesting is, if you just do the stepping, you improve 5 times. You just do the sealing, you improve your lifetime 5 times. If you do both, you can improve your lifetime not 25 times, but hundreds of times more. So this was kind of when you do combination and cross, these are things to learn. And we were able to do that. So the last modules that you've seen actually have been done with the grading and the sealing of the whole thing and achieving. Now this is still not enough. They're expecting 5,000 to 10,000 cycles, where we are now over 1,000, between 1,000 and 2,000 cycles. So this is kind of work on a power conversion. You have to go from the devices to the packaging to the system to have the whole thing work. And then you have an efficient converter. Now you put these efficient converters together to do distribution, and they do. You know, as long as there is more energy coming in than is being consumed, you're fine. But the problem is when you do with these converters that actually what you do, all of these guys that feed the loads, they just worry about the load. And all the guys that feed the source just optimize the source. But then they also need to talk to each other, and that's where the problems come. And some of these things are very simple. Like if there is a source feeding a load, there is a loading effect because the source impedance is not 0 and the load impedance is not infinite. And even worse, the load impedance could have a negative incremental character. When you increase the voltage, the current could go down because the load just consumes the power that it consumes and doesn't care if you want to give it more. And then you can have easy instabilities. And this is well-known negative impedance characteristics have been studied on a DC system. Something that we have done in the last 5 years quite extensively was applying this mathematic extension to multivariable systems that at AC systems. So that at AC systems, you also have the same issues that, you know, you should be feeding at all frequencies. The load should be either lower impedance or not interacting too strongly with the source so that the stabilities don't happen. And the question was, do they happen or not, and how to do that? The thing was that we were really asked to do that, and then when we did, this is mathematical theory, this is probably 20 years old, that actually if you do look at the impedances here in the synchronous coordinates, D and Q coordinates, and if you align D with the power flow and Q being orthogonal to that, so this kind of corresponds to the active power flow and this is reactive, that actually if you have the loads that are all power converters, they appear as constant power loads, means that at low frequencies they have some value and negative impedance, negative real value. So that's a cause or possible cause of instability. In order to see if this happens, you know, again, Boeing, when they built 787 aircraft, they were very worried that the system will not work when they put it together. And then when they did put it together, it did not work. So they kind of expected that, but they were ready and they fixed it. But one of the things they did, they did ask their suppliers to come up with impedance measurement unit because they had a spec of impedance shape that load and source have to meet. And all the suppliers said, we meet it. And they says, how do you know? It says, well, we simulated it. Did you measure it? It says, well, you measure it for me because there isn't such an instrument. So then that's how we got the contract, and we spent quite a bit of time coming up with instruments so they could do the measurements and verify that they are what they are. Spent time doing that, and did this, and helped, I hope, them. It's flying, and I hope it's not going down. But then we learned a lot. And later on, the Navy found that this happens also on submarines and some military stuff, so we have developed that for them. And that this is the last one that was funded by Navy that we are developing now and allowed us also to do the high power stuff. The essence is you're injecting perturbation in your system. This is one line diagram for a three-phase system, injecting either in series voltage or in parallel some currents, about 1 to 5% perturbation compared to the total power flow from source and load. And then you're measuring voltages and currents, dividing one by the other, or matrices to find impedances. This one was nice because we were able to use 10 kV, 120 amp silicon carbide modules in order to achieve this so that we could be switching at 20 kilohertz so that our bandwidth of injection is much higher than a power transfer, which is 60 hertz or so forth. So we could measure the things up to kilohertz. And then this was done by Cree and PowerX to build a module. The H-bridge was built actually by GE, and then we built this whole system in our lab, which consists of actually kind of modular approach. So we use this to play how we could do MMCs with silicon carbide for high power. Although the funding was for impedance measurement, we tried to kind of double up. And so we built this H-bridge, which contains capacitors, inductors, and the H-bridge itself. And that's then built of 3 of these H-bridges. And then they could be reconnected and reconfigured by this system on the top. And at the bottom, we have DC capacitor banks just in order to be able to inject the perturbations at the very low frequencies, like 0.1 hertz. And then we could, by reconnecting here, have these PEBs, power electronics building block, connected in series for higher voltage in line to line, and that's for the shunt injection when you inject relatively low currents but need to withstand high voltages. And then for series injection, you need to withstand low voltage but have very high current because the whole system current goes through you, and then you can reconnect those to work in series. Nice experiments, and with some of these, we were able actually to do the experiments. This is by Bo, who is now in Cambridge. He did this for his PhD, where he was able to measure impedance of inverter feeding a rectifier, and then to demonstrate that at these low frequencies, this green is the load, the input impedance of the rectifier. These are output impedances of the source, and then the blue one is a good source with a wide bandwidth, and then the red one is a bad source, your voltage loop that tries to regulate the AC voltage here is not a wide enough bandwidth, so you have a higher impedance at lower frequencies, and that's where the phase difference between the two could approach 180 degrees. If you plot the Nyquist plots, you could see that actually in this stable case, good output, good inverter and the load, you had, when it starts up, good behavior with the good voltage regulation here, and all AC currents are good. But actually, if you use the one that has lower bandwidth inverter here, then one of the Nyquist could circle -1, and you do go into unstable behaviors. Now, this was an interesting thing that we learned while doing that for the others, which everybody suspected. There was just, can you do an instrument that does that? And that's what we learned, that actually you can have a negative impedance in the Q-axis, and nobody was designing to control the Q-axis at all. And that's an interesting point, and that's what we learned over the last 5 years, that actually this is to a big extent controlled at low frequencies by something that's called PLL, or phase locked loop. As these converters try to synchronize each other, they actually do have problems and can have problems. As the power systems guys know, But we thought we just need to design a better PLL. But actually it turns out that it does show an impedance and you have a negative impedance there. And then if you don't do it properly, then you can have things like this. And this is a video that was, this is the voltage that's here, connected to a grid, a weak grid. And then the blue is the current going in this before it starts operating. So this is just a diode rectifier. And then the yellow is the current coming of additional source. And these two have PLLs. And now we'll start the video. And okay, at one point this one will come on, and then you will see sinusoidal. Everything becomes sinusoidal, works well. But this is these two currents, one coming here, and small current is coming from the grid. They actually finally, and this is the real time, and they just desynchronize. So what's happening actually is that this PLL tries to synchronize to that one, to itself, and to the grid. And this one tries to synchronize to this one, to itself, and to the grid. And then at the end, they can't decide whom to synchronize to. Now, if grid is extremely stiff and this is very low impedance, everything is fine. But if anything is soft, and in microgrid, everything is soft, then the things are interesting. Okay? So this is completely new, and that happened to us because we couldn't get our measurements right. They were always doing something funny. So then we learned a lot of things. Okay, let me finish with EMI, EMC. My time is a little bit running out, so I'll have to speed up. Also, at the switching frequencies, it's tough. And it's especially tough if you want to be very advanced and go, wide band gap. So this is a GaN system. We did a battery charger for the cars to get out of the airplanes a little bit. And this is a kind of bidirectional converter, isolated going single phase to the battery. And these are GaN modules where we actually, the other HRL labs developed the devices themselves, normally off GaNs at 600 volts, but not too high current rating. So we came up with paralleling a lot of those for a phase lag. And coming with a new nice structure with extremely small inductance. This is multi-layer chips. So it's very small inductance. Inductance is fraction of nanohenries, 0.1 to 0.5 nanohenries, loop inductance in a pound. So this is commutation inductance. So we did that, and it worked actually quite well. But then comes this consequence. Your common mode noise is so high, you're actually burning the wires. And this is controller that should have been sitting on top of that. That was impossible. And then you put it aside, and you have to put so many common mode chokes and filters for just your processor to work, that actually your filtering for your processor to work is bigger than all the capacitors and power magnetics that you did. So that's something to think about next time you do it. We somehow convinced the sponsor, ARPA-E, that they should not look at this. They should just look at this and see how good it is. But okay, the one that I've just shown, PEB, we're just testing that now in Florida, collaborating with another university. These are the common mode currents measured on a system. We had huge problems. Our control system was tripping all the time. Okay, the system is designed to do the injection of the currents of about 100 amperes. The common mode currents exceed 200. This is just parasitic currents going through your ground. Okay? Basically, when you start going to full voltage, nothing works. Everything stops, including your scope and whatever else you had around it. So we're still debugging this and spending a huge amount. That's kind of points we need to be doing and understanding these things from the beginning much, much better before really we can implement this in the systems. So this shows something that was funded by a French company when they want to do silicon carbide, but what about EMI? Can I make a motor drive and predict what junk is going to be there so I can do something about it? It never leaves this thing and spoils my airplane. So this is time we did, this is a commercial drive. You put in some test setup where you change the known impedances, and that's how you can develop kind of linear model of this. So you measure those things there and then come back with a linear model, some equivalent impedances and equivalent voltage sources or noise sources. And that should be able to predict your things at a given operating point quite well. We were at the end able to do that for common mode and in some cases for differential mode noise as well. that if you have a good model of impedances that you connect on that side, impedance to get to the next side, this model works very well. And whatever you connect, if you have a model of that, you could predict the noise going out on both sides. And this was interesting because not just an input would normally look at EMI, but on both sides. And so this is, changing the cable, the noise can change, and you can predict it very well. Changing the impedance of your network, the noise can change substantially, and you can predict it well. Putting the filters on one side or the other side, the predictions go well. And this enables us to look at the system level issues of the power converters. Although we developed all of this very nicely, the system in Florida we delivered still doesn't work. So we're modeling and trying to see what to do. The filter that I was shown here, this is an interesting point. We put this to integrate and make it very small to achieve high density. Actually, it doesn't work. It's just a nice picture. And then we figured out why it doesn't, and everything was funny. EMI was horrible everywhere. So we did build just a simple inductor with a whole lot of turns around it. And then looked at it and look at a field. This is a probe to measuring X, Y, and Z. And it's quite symmetric around it. This is looking, like this, and this is Z, what's going up. And quite symmetric, but it was at 500 kilohertz excitation put here. It's interesting when you put at 5 megahertz or even higher, 20 megahertz, this plane is symmetric, but actually, no, sorry. This plane is symmetric, but what's going up actually becomes like a bipole magnetic. And why is that so? We were puzzled, spent about 2 years being puzzled, and then we said, let's go and look at the textbook. And we did the measure field for each turn with a much more sensitive probe, and then actually measuring current turn by turn. And then when we did that, we figured out at 500 kilohertz, the current everywhere is the same. At very high frequency, the current actually reverses at the opposite side where it enters. It goes in the wrong direction. Now, okay, how does that work? And actually, it's not that complicated. Once you figure it out, it took us almost 2 years. It's just capacitances go around, so the current doesn't just go through the windings, they also go through all the parasitic capacitances. And then you can even go in a MATLAB and use BSR law and predict the things that at 20 megahertz, yes, it's exactly what you measured. As we were taught in our, whatever, third or fourth year of college, but it takes some time to figure it. Based on that now, you could do integration, but actually you have to know how to orient the things. And when you do this functional and structural integration, there are a lot of things to relearn, both electromagnetic as well as thermomechanical. And this is the last slide that I have on this. At the end, how do you impact the system? This was funded, I can't say by whom, but anyway, can I predict the size and weight of the whole system based on everything I know, what I talked so far? It's a tough one, but Bowen still also did this for his master's degree, that this is kind of a sample system where you have multiple loads, AC, DC, generator, and this is the AC distribution, and then you can adjust different voltages or different currents of the system and then redesign, rough design, using algebraic equations, all the components, filters, converters, everything, rough design. They won't work based on that design, but we hope that this is relatively reasonable weight estimate. And then you go and repeat that, you can choose the frequencies and so forth. And you repeat that for a DC system, and then you find out that the DC system is slightly lighter than the AC system. And at the end, you probably build and prove that it's wrong because the difference is too small. And your error is probably 50%. But anyway, going back to the modeling, if you are optimizing, it's not optimizing inductor, it's optimizing the system. But how to connect optimization of inductor with the system? A lot of work, and I'm happy that you're doing it. I just hope that that funding will not disappear. That's the biggest problem of this. I have been doing this 5 times over my career, every time for 2 or 3 years and then stopping. And many other people have been doing the same. The key to my point, if we really want to have a progress on these design tools, there has to be a big consortium over 10 years or more just doing that and solving all the intractable problems. Okay, at the end, CPES, what we are very happy with and very thankful, this was funded by the companies that support us. We now have a consortium of 84 companies. And that's very nice. And what's even nice is that this money they are giving, this is a gift money. So they give us whatever we do as long as we do something good. But that's nice. You usually get that type of money from government, rarely from industry, and this works really nice. I hope you guys will be able to build on that experience, and I will be glad to share that with you. And at the end, you know, I asked what's the future of Pollock Tronics, and the first slide I'm finishing, I think it's very good. I think it will be essential for societal energy needs from organ implants. We're not working on that, but this is a beautiful place because that's the place where people don't care what they pay. And you can overcharge and be rich if you're doing this, and I don't think we're doing enough of this. And that this is we're doing because we have to do, because we screwed up already, so we're fixing what we screwed up. But I think the future is bright. And I think it's bright also because of this.
What we're calling the Next Generation Power Electronics Innovation Institute is bringing together leading companies, universities, and federal research all together under one roof. Folks at this hub are going to develop what are called wide bandgap semiconductors.
Okay. If President can say these words, I mean, just pronounce them, I think our future is bright. You just have to get David Cameron to say the same words, and it's great. Thank you very much.